Crossing an ocean has traditionally meant choosing between storm-swept bridges or the dark, concrete-lined rock of a standard tunnel. This vision proposes a different journey, a path of transparency that brings the passenger directly into the marine environment. This engineering fantasy finds its setting along the rugged coastlines of Japan, a country where coastal infrastructure must be designed for extreme currents and seismic activity. The deep sea is a high-pressure environment. Standard glass structures would buckle under the weight of the water and the sheer force of deep ocean currents. To withstand these conditions, the project moves away from terrestrial architecture and adopts the logic of deep-sea marine engineering. Before construction begins, survey vessels sweep the route, mapping the seabed landscape and measuring soil stability to ensure the floor can carry the weight of the structure. Remotely operated vehicles descend to the seabed, providing high-resolution scans of the terrain at depths that are inaccessible to human divers. On the coast, the landside preparation begins with the construction of access roads, power stations, and deep excavations to receive the tunnel entrance. The initial approach tunnels are built using traditional civil engineering, featuring reinforced concrete, waterproof sealing membranes, and heavy rock bolts. These heavy concrete sections provide the structural anchor points required to connect land-based rail networks to the transparent modules offshore. The transparent modules are engineered as continuous cylinders, avoiding the structural vulnerabilities found in flat, rectangular shapes. A circular cross-section is essential because it distributes external water pressure evenly across the entire surface, preventing the stress concentrations that would shatter a flat pane of glass. This geometry is supported by a skeleton of machined titanium rings and longitudinal ribs designed to maintain the tube's shape under extreme load. Curved, multi-layer glass panels are then inserted into the grooves of the titanium rings, building the transparent wall piece by piece. Every seam is double-sealed using compressed polymer gaskets and an application of anti-leak gel to ensure the joints remain watertight. The assembly takes place in specialized coastal facilities where heavy lift cranes move the completed modules through the final stages of manufacturing. By utilizing circular geometry and titanium reinforcement, the design transforms glass into a material capable of surviving the deep ocean. Before reaching the ocean, each module is placed into a testing cradle to simulate the forces it will encounter on the seabed. High-pressure pumps fill the chamber with water to mimic the weight of the ocean at the project's maximum depth. Sensors monitor the module for flange movement, seal deformation, or any sign of stress in the multi-layered glass. This inspection provides the final verification that the glass and titanium assembly can withstand the calculated pressures of the seafloor. Offshore, floating cranes and transport barges gather over the route to begin the installation phase. The modules are lowered through the water column and aligned with locking grooves on the pre-laid seabed foundations. Hydraulic clamps secure the module while gasket rings are compressed between the flanges to create a continuous, watertight corridor. Once the physical tube is complete, a small unmanned inspection vehicle is the first to travel the length of the track. This drone records data on rail alignment, vibration levels on the isolation pads, and the performance of the leak detection sensors at every joint. This testing phase provides the empirical data needed to verify the tunnel's safety systems before it is cleared for passenger service. The raw construction environment is eventually replaced by a finished interior. Blue lighting along the titanium ribs emphasizes the curved architecture of the tube. For the passenger, the journey begins on a standard high-speed train that glides out from the coastline and into the undersea section. Inside the tunnel, the cylindrical glass walls reveal the deep blue of the ocean and the slow movement of marine life outside. At high speeds, the motion of the train creates a shifting play of light across the curved titanium and glass surfaces. The project combines the practical requirement of high-speed transit with the immersive perspective of an underwater observatory. This visionary passage suggests that the infrastructure of the future might do more than move people between destinations. It can change how they perceive the world through which they travel.